Indices, created by a mathematician known as John Napier, are a really useful way of writing repeated multiplication in a much faster and efficient manner. What we have here in the example is we have 6 to the power of 2, or 6 squared. 6 is known as our base, and 2 is known as our power, our index, or our exponent. What it actually means, and what this power actually means, is that we have 6 times 6, because we have 1 and then we have 2 6's. Again, it's all based on repeated multiplication. The first law that we are going to look at is multiplication. Rather than giving you the formula straight away, we are actually going to work out how you create a formula for using indices and multiplication. A really important property of indices is that when you're dealing with indices, they must have the same base. In this example, that is 6. They're both the same, so therefore we can actually use these laws. If we were to write out 6 squared, what we would get is 6 times 6. We have our multiplication sign. And if we were to write out 6 cubed, we would have 6 times 6 times 6. If we go back to the underlying principle of indices, it's all about repeated multiplication. If I count how many 6's I have 1, 2, 3, 4, and 5. And therefore, I could call this 6 to the power of 5. Well, if I go back to my original and I look at my indices or my powers, what operation could I do with 2 and 3 that would get me 5? Well, obviously, that is addition. So therefore, if I was to create a general rule, when I multiply my two indices, I add the powers. So our rule would be a to the power of m multiplied by a to the power of n will give us a to the power of m plus n. A is any base as long as it's the same. This can be a number or an algebraic variable. M and n again are powers or exponents or indices, which again can also change, can also be algebraic or numerical, and all we are simply going to do is add them together. The next law we are going to look at is division. Once again, we are not going to write out the general rule, but we are actually going to see how it works and then create it. Once again, I'm going to go back to the underlying principle of indices and this idea of repeated multiplication. 6 to the power of 4 would look like 6 times 6 times 6 times 6, and it would be divided by 6 times 6. Now what I want you to do is I want you to take a number in your head between 1 and 10. I want you to multiply it by 3, and then I want you to divide it by 3. What you will notice is actually you end up back with the number you started with. The reason for this is that multiplication and division are the inverses or the opposite of each other. So in this example, what we have is we actually have a number of cases where we are multiplying by 6 and we are dividing by 6. As you can see, what I can do is I can cross off this 6 and this 6, because multiplying by 6 and dividing by 6 is just like multiplying by 1, which doesn't change anything. And I can do it again because I have 2 on the bottom. Going back to my laws of indices, on top I now have 6 times 6, which I can call 6 squared. Generating the rule. So, if I go back to my example and I look at my powers one more time, I have 4 and I have 2. What operation can I use with 4 and 2 to get me 2 as an answer? Well, quite simply, that will be subtraction. So, our general rule will be, in division, a to the power of m divided by a to the power of n is equal to a to the power of m minus n. Once again, a is the base, numerical or algebraic. M and n are powers or exponents or indices, whatever way you want to call them. And what we're going to do is we're just going to subtract them. One key note here. If the index on the bottom is negative, so for example, if you had 6 to the power of 3 divided by 6 to the power of negative 2, you need to realize that actually that will give you 6 to the power of 3 minus negative 2, which in fact will become positive. So you would get 6 to the power of 5. That is the one very important note that you need to make sure that you take on board when you're doing division. The next law we're going to look at is raising a power to a power. And once again, we are going to go back to the original idea of what indices actually are, and it's all about repeated multiplication. If I was to write out 6 squared to be cubed in a longer version, what we would get is 6 squared times 6 squared times 6 squared. If I wanted to, I could now use the first law, multiplication, and add all my powers together to give me 6 to the power of 6. Alternatively, I could write out what 6 squared actually means. It means 6 times 6, and again 6 times 6, and again 6 times 6. What I have is 1, 2, 3, 4, 5, and 6. Once again, just to double check, giving me an answer of 6 to the power of 6. Just like all the past examples, we are now going to go back to our indices, our index, our exponents, and see what operation takes place when I raise a power to a power. Well, clearly, 3 multiplied by 2 will give me 6. As such, the general rule in this case, when you raise a power to a power, you multiply the indices or the exponents or the powers or whatever you would like to call them, and we have a to the power of m raised to the power of n is equal to a m n, which essentially means we multiply the two indices together. For this law, we are going to look at the idea of anything to the power of 0 is equal to 1. This is probably my favourite one to actually explain because it's the one that seems the most obscure to people, yet has a really simple explanation. 6 to the power of 1 is 6. 6 squared is 36. 6 cubed is 216. And 6 to the power of 4 is 1296. If we look at what's happening each time, in fact, we are actually multiplying by 6. Yet, if we went in the opposite direction, so if we look at what's happening as we go the opposite way, we are in fact dividing by 6, because, once again, multiplication and division are the inverses of each other. Well, if we were to continue this trend, 6 divided by 6 will give me 1. And then if we look at the left-hand side of our equations, we have 6 to the power of 4, 6 to the power of 3, 6 to the power of 2, 6 to the power of 1. And if we continue on our pattern, we actually get 6 to the power of 0, which is equal to 1. This pattern holds true for all examples in general. And as such, our general rule is a to the power of 0 is equal to 1. And a, of course, can be any base, numerical or algebraic. There is one other way that we could also prove this, using some previous laws of indices. For example, if you had 3 divided by 3, it's very easy to identify that that's actually 1. Well, if you were to look at the powers of those 3's, you would have 3 to the power of 1 and 3 to the power of 1. Well, when we divide, we actually subtract our indices. So therefore, 3 to the power of 0 would equal 1. And as such, there's another way to prove 3 to the power of 0 or anything to the power of 0 is equal to 1. This will be the last law in this video, raising a power to a product. What we have here is we have 2x to be cubed. The product is occurring here because you have 2 times x. Once again, if we were to write this out in its most basic form, what we would have is 2x multiplied by 2x multiplied by 2x. And what we could then do is actually going back to what indices actually mean. If we were to count up what we have, well, we have 1, 2, 3 2's. So we have 2 to the power of 3, and we have 1, 2, 3 x's. So we have x to the power of 3. If we wanted to, we could change 2 to the power of 3 to 8, and then once again just keep x cubed on its own. What we notice is actually when we are raising a power to a product, we need to make sure that we apply the power to both elements or both terms within the bracket. As such, we had the power of 3 on the outside, giving us 2 to the power of 3 and x to the power of 3. Our general rule is, if you were to have a b to the power of n, that is a to the power of n by b to the power of n. This can be used if there are more than two products occurring in a bracket that's being raised to a power. For example, if you were to have something like ABC, so if you had ABC to the power of 4, this would be a to the power of 4 by b to the power of 4 by c to the power of 4.